Welcome back to the deep dive. We have a really interesting stack of documents today. We're moving away from the abstract theories of how the internet connects us all and getting right into the trenches.
Right into the nuts and bolts.
Exactly. We're looking at network security, specifically IPv4 access control lists or, ACLs.
Yeah, this is where the rubber meets the road. Or I think a better analogy is probably where the bouncer meets the club patron.
The bouncer analogy is actually perfect because when I was reading through these guides, everything from the configuration basics to some of the troubleshooting nightmares, I couldn't shake that image.
Mm-hmm.
We usually think of a router as this helpful traffic cop.
Right.
Just waving cars through, you go here, you go there. But in ACL, it turns that router into a security guard with a clipboard.
And a very strict one at that.
Extremely strict. It's checking IDs, it's checking what you're wearing, it's checking who you're with. And if you aren't on the list, you don't just get turned away. You technically cease to exist as far as the network is concerned.
That's the reality of packet filtering. It's the most fundamental layer of security we have on a router. Before you get to fancy firewalls and intrusion detection systems, you have the humble ACL.
So here's the mission for this deep dive. We need to demystify how these lists actually work. It's not enough to just know the commands. The sources make it really clear that you have to understand the logic of the router.
Right.
We're going to look at the difference between the standard lists, which seem to be a bit of a blunt instrument, and the extended lists, which are more like surgical tools.
And we definitely need to talk about where you put them. Because if you put a bouncer at the wrong door, you might accidentally lock everyone out of the building.
Including yourself.
Including yourself.
Which sounds like a very bad Monday morning. So let's start with the absolute basics. When we say access control list, physically on the device, what are we looking at?
Physically, it is exactly what it sounds like. It's a sequential list of instructions. We call the individual lines ACC's access control entries. Yep. You create this list line by line, and then you apply it to a specific interface on the router.
And the direction matters, right? I saw a lot of bold text about inbound versus outbound.
Crucially, you have to tell the router, apply this list to traffic coming in from the wire, or apply this to traffic trying to go out to the wire. If you don't specify the direction, the list is just a text file sitting in memory doing, well, nothing.
Okay, but here's the part that really stood out to me in the documentation. The order of the list isn't just for organization, it's functional. The sources keep mentioning first match logic. Walk me through that.
This is the most common place where engineers trip up. So imagine a packet hits the router interface. The router pulls up the ACL and starts at the very top line 1. It compares the packet to the rule. Does it match?
And if it does?
If it matches, the router executes the action immediately, either permit or deny. And then this is the key. It stops.
It just stops.
It stops reading the list.
It doesn't check the other rules, even if there's a more specific rule further down.
Never. It's like a checklist where you're only allowed to check one box. Once you find a match, you're done. You exit the logic loop entirely.
So let's play that out. If I have a rule at line 1 that says permit everyone, and then a rule at line 50 that says deny Bob.
Bob is getting in every single time. The router sees permit everyone, matches Bob's packet to everyone, allows him in, and stops reading. It never even sees line 50.
That seems like a recipe for disaster if you aren't paying attention. You really have to put your specific exceptions, the deny Bob rules, at the very top before the general rule.
Exactly. Specifics first, generals last. If you do it the other way around, your specific rules become what we call shadowed rules. They exist in the config, but they can never actually be reached.
Now, what about the opposite scenario? A packet runs the gauntlet. It goes from line 1 all the way to line 100, and it doesn't match a single rule. What happens then?
It gets dropped.
Just like that. Yeah. No error message, no try again.
Just silence.
Yeah.
This is the concept of the implicit deny. There's an invisible rule at the bottom of every single ACL in existence. You can't see it in the configuration, but it's there. And it says, deny all.
That feels incredibly harsh. Why is the default setting destruction?
It's a security philosophy. It's called zero trust in modern terms, but the logic has always been there. It implies that unless traffic is explicitly allowed, it is forbidden.
So if you didn't say yes, the router assumes no.
Precisely. It prevents you from accidentally leaving the back door open just because you forgot to lock it. In this case, the door is welded shut unless you carve a keyhole.
Okay, so we understand the mindset. Now let's look at the tools. The source material divides ACLs into 2 main camps, standard and extended. Let's start with standard. They use numbers 1 through 99. Why did the notes call these a blunt instrument?
Because they are nearly blind. A standard ACL can only look at one piece of information in the packet header.
And that is?
The source IP address.
That's it. It doesn't know where the packet is going.
Nope. Doesn't know the destination, doesn't know if it's an email or a Netflix stream, doesn't know which port it's using. It just looks at the ID card and says, oh, you're from 192.168.1.5. Okay, rule applies.
So it's a bouncer that only checks your home address but doesn't care if you're trying to enter the VIP lounge or the bathroom.
That's a good way to put it.
Mm-hmm.
And because it's so limited, it creates a massive dilemma on where to place it in the network.
Ah, the golden rule of placement.
Right. If you're using a standard ACL, you must place it as close to the destination as possible.
Explain that logic to me, because intuitively, I would want to stop bad traffic as soon as it enters my network. Why drag it all the way to the destination?
Think about the Bob scenario again.
Yeah.
Let's say Bob is at the main office, and you want to stop him from accessing a specific sensitive server at the branch office. But Bob is an employee. You want him to still be able to, check his email, browse the web, print documents.
Okay, sir.
If you use a standard ACL, which acts purely on the source, Bob, and you put it at the main office router right next to Bob.
It kills everything.
Exactly. The router sees a packet from Bob, checks the list, sees deny Bob, and drops it. It doesn't care that Bob was just trying to go to Google. Because the standard list can't distinguish the destination, you've completely cut him off from the world.
I see. So because the standard list can't distinguish what Bob is doing, only that it is Bob, you have to let him travel all the way across the network to the branch office. And only when he tries to enter that specific router connected to the sensitive server do you stop him.
Correct. It prevents collateral damage. You accept the inefficiency of transporting the packet just to ensure you don't accidentally block legitimate traffic.
That seems manageable but annoying. And I assume that's why we have extended ACLs.
That is exactly why. Extended ACLs numbered 100 to 199 are the precision tools.
So what makes them so different?
They can see everything. They check the source IP, yes, but they also check the destination IP. They check the protocol, TCP, UDP, ICMP, and crucially, they check the port numbers.
So this is where I can get granular. I can say, Bob is allowed to talk to the server, but only if he's trying to view a web page on port 80. If he tries to use FTP on port 21, block him.
Exactly. And this introduces the concept of the ND requirement. In a single line of an extended ACL, you're defining all these parameters. For the rule to trigger, everything in that line must match. Source AD destination and protocol and port.
If even one tiny thing doesn't match, like if the IP is right, but the port is 443 instead of 80.
The router skips it and goes to the next line immediately. It's an all or nothing match for that line.
The notes mention some math here that I want to dig into. To define these IP addresses, source and destination, we use something called a wildcard mask. And frankly, looking at the examples, it looks backward compared to everything else in networking.
It feels backward because it's the inverse of a subnet mask.
Yeah.
We often just call it an inverse mask.
Right. In a subnet mask, the ones mean network and zeros mean host. But here,
in a wildcard mask, the 0 means check this bit, it must match exactly. A 255 means I don't care, ignore this part.
So if I have an address 192.168.1.1 and a wildcard mask of 0.0.0.
All zeros. That means match 192 exactly, match 168 exactly, match 1 exactly, match 1 exactly. You are identifying one single specific host.
Oh, okay. And the documentation says there's a shortcut for that.
Yes, thank goodness. The host keyword. So instead of typing that mess of zeros, you just type host 192.168 on point 151. Much easier.
Much easier. Now, what if I want to match a whole subnet, say 192.168.1 dot anything?
Then your mask would be 0.0.255. The zeros say the first three numbers must match. The 255 at the end says the last number can be anything.
Is there a trick for calculating this? Because doing binary inversion in your head during a network outage sounds like a bad time.
There is a very simple math trick. Take the number 255.255.255.255 and subtract your regular subnet mask from it.
Just basic subtraction.
Simple subtraction. If your subnet mask is 255.255.255.550, you do the math. 255 minus 255 minus 0 is 255, so you get 0.0.0.255. That's your wildcard.
That I can do. Okay, so we have these precise extended ACLs. We can identify source, destination, specific port. How does this change the placement rule?
It flips it completely. The golden rule for extended ACLs is place them as close to the source as possible.
Because now we don't have to worry about collateral damage.
Exactly. You can write a rule that says, deny Bob from accessing the branch FTP server. You can put that rule right on Bob's local router. Because the rule specifies the destination, it won't block Bob from going to Google. It only triggers if he heads for that specific server.
And the benefit there is efficiency.
Huge efficiency. Why let a bad packet travel across your expensive WAN links, taking up bandwidth, only to drop it at the far end, kill it at the source? It saves resources and reduces network congestion.
So quick recap on placement. Standard is blunt, so put it near the destination to be safe. Extended is precise. Put it near the source to save bandwidth.
You got it. That's the golden rule.
Let's shift gears to managing these things. Because looking at a list of numbers, access list 101 permit, that seems like a nightmare to maintain. 6 months from now, how do I know what list 101 is even supposed to do?
You don't, unless you have a photographic memory. And that's why the industry has largely moved to named ACLs. Instead of a number, you give the list a string name, like guess Wi-Fi restrictions or block FTPass.
That seems infinitely more human readable.
It is. It uses the same logic underneath, but it makes troubleshooting so much faster. You know exactly what the list is intended to do just by looking at the name.
Speaking of troubleshooting, the old way of editing these lists sounded absolutely horrific. The sources describe it as a nightmare.
Oh, it was. In the old days, with standard numbered ACLs, if you had a list of 50 rules and you realized you needed to delete rule number 10, you couldn't just delete rule 10.
You're kidding.
I wish I was. You had to copy the configuration into a text editor, delete the line, then delete the entire access list from the router, and then paste the whole thing back in.
And during those few seconds where you deleted the list, the router is just wide open.
Or closed shut, depending on how it fails. But yes, it was incredibly high risk. You're essentially doing open heart surgery just to remove a mole.
Thank goodness for progress. How do we do it now?
Sequence numbers. Modern iOS assigns a number to each line, usually in increments of 10. So line 10, line 20, line 30.
Like line numbers in code.
Exactly. So now if you want to get rid of line 20, you just type no 20. Boom, it's gone. The rest of the list stays put.
And I can insert things. Let's say I forgot to block Bob and I need to put that rule at the top.
Yes. You can insert a rule at sequence number 5 or 15. This is huge because of that first match logic we talked about.
Right.
If you discover a security hole, you can surgically insert a deny rule right at the top without rebuilding the whole structure.
That brings us to verification.
Right.
So we've built the list, we've applied it. How do we know it's actually working? Is there a way to see the bouncer in action?
The best friend of any network engineer.
Yes.
Show its access lists.
What does that show us?
It shows the list, obviously. But next to each line, it shows a counter, matches. It tells you how many packets have hit that specific rule.
That seems incredibly useful for debugging. If I write a rule to block Bob and the counter stays at 0,
then either Bob isn't trying to connect or you messed up the rule. Maybe you got the IP wrong or the wildcard mask is off. Something's not right.
or if I see the implicit deny counter skyrocketing.
Then you are blocking a lot of traffic you didn't explicitly account for. Maybe you forgot to permit the legitimate users and they are all hitting that invisible wall at the bottom.
The notes also mention a log keyword.
Yeah. You can add the word log to the end of any rule. If you do that, the router will spit out a system message every time that rule is triggered. Packet from X to Y denied.
That sounds great for catching a hacker. Or just figuring out who is trying to access the server.
It is, but be careful. Logging takes CPU power. The router has to stop what it's doing and write a message. If you put a log command on a rule that handles, say, a high-speed video traffic, you can literally crash the router's processor.
So use it for debugging, but maybe don't leave it on forever.
Exactly. Turn it on, find the problem, turn it off.
One last gotcha before we wrap up. We talked about direction earlier. Inbound versus outbound. The sources imply this is where even the pros get confused.
It is the most common mistake. You write the perfect ACL, the logic is sound, the wildcard masks are perfect, but you apply it to the wrong side.
How should I visualize this? Because looking at a diagram, lines go in and out everywhere.
You have to stand inside the router. Imagine you are the processor. Inbound is traffic hitting your face coming from the cable. Outbound is traffic you have already processed and you are handing off to the cable to leave.
So if I play a filter outbound on an interface,
That filter only checks traffic leaving that interface. So if you are trying to block traffic coming in from the internet and you put the ACL on the outbound side, the traffic walks right past the bouncer before he even checks his clipboard. It's already inside the router before the check happens.
you really have to trace the path of the packet on a diagram.
Always draw it out. If you don't draw it, you will mess it up. I've seen seasoned engineers bring down networks because they flipped in and out.
So let's look at the big picture here. We've gone from the logic of the list, that first match rule, to the difference between the blunt standard ACLs and the precise extended ones.
And the importance of using named ACLs and sequence numbers so you don't lose your mind editing them.
It really highlights that being a network engineer isn't just about memorizing syntax. It's about understanding flow. It's about logic.
It is. And I think the most important takeaway is that concept of the implicit deny.
The default no.
It's not just a technical default, it's a mindset. Security shouldn't be about listing all the bad things in the world and trying to block them. That's impossible. Security is about defining what is necessary, allowing only that, and assuming everything else is dangerous.
If I didn't say you could do it, you can't.
Exactly. Does that make the network harder to manage? Maybe. Does it make it safer? Absolutely. In this game, convenience is usually the enemy of security.
Something to think about the next time your connection gets dropped. Maybe the router is just doing exactly what it's told to do. Thanks for listening to this deep dive into ACLs. We'll catch you on the next one.